Good morning, students. Once again, I welcome you all for this session. So, in the previous class, we have solved one problem on type 2, that is finding out area of tension reinforcement and area of compression reinforcement. So, let us solve one more problem. Okay, so the problem is like this: doubly reinforced rectangular beam of size 300 mm by 600 mm, simply supported at both ends. The effective cover for both tension and compression steel is 35 mm. The effective span is 6 meter. The beam carries a service imposed load of 24 kilonewton per meter and superimposed dead load of 16 kilonewton per meter. Okay. Use M20 concrete and HYSD steel Fe415 grade. Determine the tension and compression reinforcement. So the problem is like this. Now first write down the given data. So diagram you can draw. So width of the beam, then overall depth. This 600 mm is overall depth, 300 mm is width of the beam. So this is compression steel provided at the top, and this is tension steel provided at the bottom. So now we have to find out what is AST and what is ASC. Okay, the cover for both the ends, for the steel it is a 35 mm. This is D dash from top to center of this compression steel D dash, and this is also effective cover, that is 35 mm. So from this we can find out small d. So small d is what? Capital D minus this 35 mm. Okay, so B is 300 mm, capital D is 600 mm, then effective depth small d is equal to 600 minus this 35, we'll get this small d. Then effective span, length of the beam is given 6 meter. Then live load is given. Live load on the beam is given 24 kilonewton per meter. Then superimposed dead load is also given. Okay, it is given 16 kilonewton per meter. Okay, then M20 means FCK is 20 Newton per mm square. Then Fy is 415 Newton per mm square. So first we will find out the total load. Okay, so first given is this superimposed load is given, dead load. Okay, superimposed dead load is 16. Then live load is given 24. Then one more we are going to find out. We know the cross section of the beam, so we can find out self weight of this beam. So first dead load or self weight of the beam is equal to total area. So B into capital D into density of RCC. So B is 0.3 meter, 300 mm means 0.3 meter, then capital D 0.6 meter, then this 600 mm means 0.6 meter into density of RCC is 25 kilonewton per meter cube. So see, this is in meter cube. It is in meter, so that's why we are substituting these two also in meter. So 0.3, 0.6 into 25 kilonewton per meter cube. So this total dead load of or self weight of the beam comes out 4.5 kilonewton per meter. So this is in the form of UDL. Okay, and this is given in the problem. Superimposed dead load, it is 16 kilonewton per meter. Then live load, it is 24 kilonewton per meter. So if you add this total, we'll get small w. Okay, working load. So total load W is equal to 44.5 kilonewton per meter. Okay, this is in the form of UDL. Now this is small w. I want factored load or ultimate load. Ultimate load or factored load is equal to what? That we indicated as WU. So factored load W is equal to this W into 1.5. Okay, we'll multiply factor 1.5. So this WU, that is factored load or ultimate load, is equal to 66.75 kilonewton per meter. So this is the load. So once if you get the total load, we can calculate the bending moment. So since it is a simply supported beam, so subjected to UDL throughout the span. So what is the maximum bending moment at the center? It is WL square by 8. So maximum bending moment or factored moment MU is equal to, okay, WU L square by 8. Okay, if you are substituting WU, directly you will get MU. If you substitute W here, we will get M. then multiply 1.5, we'll get mu. But directly here Wu we are substituting, okay, Wu L square by 8. So this moment will be 300.37 kilonewton meter. Okay, kilonewton meter. This is the factored moment mu. Next, now we know that the grade of steel is Fe415. So for this grade, we are going to find out mu limit. Okay, maximum moment of resistance. That is mu limit is equal to, for Fe415 grade steel, what is mu limit? It is 0.138 FCK BD square. Okay, substitute 0.138, FCK is 20, B 300 and D effective depth 565 square. So this mu limit is equal to 264.32 kilonewton meter. Now right now we have the two values. One is mu, this mu, and now it is mu limit. Compare these two. So comparing mu and mu limit, now here mu is greater than mu limit. So this mu is 300.37, okay, and this is 264. So mu is greater than mu limit. This indicates what? This beam is doubly reinforced beam. Okay, the beam is doubly reinforced beam. Then next is area of compression reinforcement. ASC we have to find out. Okay, ASC we have to find out. So now we know that total mu, okay, the total moment of resistance of doubly reinforced beam is equal to, okay, mu limit, that is for singly reinforced beam, plus mu2, that is for moment for steel beam. So mu1 plus mu2. So mu1 means mu limit. So therefore total mu is equal to mu limit plus mu2. Moment is equal to, okay, force into perpendicular distance. So force is what? Stress into area. Force is stress. Stress is FSC. Area is ASC. That is steel beam you have to consider here. For this mu2 you have to consider steel beam. For mu limit you have to consider, okay, singly reinforced beam. So stress FSC into area. Okay, this is force into perpendicular distance. D minus D dash will give moment. So what we want? We want ASC. Therefore ASC is equal to this mu minus mu limit divided by FSC into D minus D dash. So here mu is known, mu limit is known, but first you have to find out FSC, that is stress at the level of compression steel. Okay, so FSC we have to find out. For this we will going to refer the table number F, page number 13, SP16 code book. Okay, for that what we require? First you have to find out a ratio D dash by D. So D dash 35 mm, D effective depth 565. So this ratio is 0.062. This ratio is 0.062. Then if you go to the table F, okay, page number 13, SP16 code book. Okay, then you will get the table like this. So for two grades of steel, that is 415 and 500 grade steel, then this here it is D dash by D ratio. Now D dash by D ratio, if it is 0.05, 0.10, 0.15 and 0.2, and for these D dash by D ratios, the values FSC, these are the FSC values. FSC values are for Fe415 grade steel, for 0.05 D dash by D ratio it is 355, for 0.10 it is 353, like this. Now what is our D dash by D ratio in this problem? That you have to see. 0.062. Now is there any value 0.062 here directly? No. So direct values are 0.05, 0.10, 0.15 and 0.20. So it is not like that. So directly we are not going to get this. So what we are going to do here is, now see, just we can write down where it comes, D dash by D and FSC value. Now see, this 0.062, okay, is in between 0.05 and 0.10, correct? So this value is in between these two. It is between 0.05 and 0.10. So 0.05, for 0.05 how much? For Fe415 grade steel, FSC is 355, and for 0.10 FSC is 353. So 0.05 it is 355 and 0.10 it is 353. But what is the D dash by D ratio in this case? It is 0.062. 0.062 in between these two. So what is the FSC value? We have to interpolate this now. So only we have to consider these values now. Now this is the reference I am going to take from this. Okay, so FSC is equal to 355 is the reference. So 355, and see this value is decreasing. 355, next it is 353. So we'll get minus. So 355 minus difference of these two. Okay, 355 minus, why minus? It is value is decreasing. So minus difference of these two, that is 355 minus 353 divided by difference of these two, that is 0.10 minus 0.05, okay, into difference of these two. We want this value, no? Reference we have taken this line. So difference of these two, that is 0.062 minus 0.05. Okay, this will give FSC. So what you have to take? This is a reference, 355 minus, okay, difference of these two divided by difference of these two, okay, into difference of these two. Okay, so this FSC value will get 354.52 Newton per mm square. Okay, so substitute this value here. So substitute this value here, we'll get AST. So therefore ASC, that is area of compression steel, ASC is equal to, substitute all the values, we'll get 192 mm square. So area of compression steel required is 192 mm square. Then next, area of tension reinforcement, AST. So we know that total AST, okay, total AST is equal to AST1 plus AST2, okay, AST1 plus AST2. Now first we'll find AST1, then AST2, add these two, we'll get total. Now again for Fe415 grade steel, okay, XU max upon D ratio, that is 0.48. Okay, so therefore XU max is equal to 0.48 into D. Okay, that is 0.48 into 565 mm. So therefore XU max will going to get 271.2 mm. Okay, XU max or maximum depth of neutral axis is 271.2 mm. And now to find out AST1 first, okay, we have to equate total C is equal to total T, that is for singly reinforced beam. First beam we are going to consider first singly reinforced beam, AST1, where AST1 is provided. So concrete force is 0.36 FCK B into XU. Okay, that is a stress into area. Stress into area is force. So 0.36 FCK is a stress in concrete, area of beam, that is B into XU. Okay, then second, equal to total tensile force in the singly reinforced beam, that is 0.87 Fy is the stress into area is AST1. Okay, so this is the singly reinforced beam. So from this you can find out AST1. Okay, so AST1 is equal to what? But one thing remember here, so in the singly reinforced we are providing maximum steel. Okay, AST1 we are providing, and this will going to consider maximum moment, that is MU limit. Okay, so here we can put in place of XU max you have to put. Wherever XU is there, here you can put XU max. So therefore 0.36 FCK B into XU max is equal to 0.87 Fy AST1. So we can get AST1 is equal to 0.36 FCK B into XU max divided by 0.87 Fy. So substitute all the values. XU max we can substitute from this. So remaining things are known. AST1 will be 1622.5 mm square. 1622.5 mm square. This is AST1. Okay. Similarly, we know that now we have to consider the steel beam. Again, equate the force in the steel beam. Concrete force in the concrete is equal to force in the steel. So 0.87 Fy AST2 is equal to, so what is a force in the compression steel, that is FSC into ASC, stress into area. Okay, so therefore AST is equal to FSC into ASC divided by 0.87 FR. So again substitute all the values here. We will get AST2 is equal to 188.43 mm square. Okay, so this is AST2, this is AST1. Add these two. Okay, add these two reinforcement, will get the total AST, which is provided at the bottom of doubly reinforced beam. So total AST is equal to AST1 plus AST2, will get 1810.9 mm square. So this is the total AST. So here we can find out ASC and here we can find out AST. Okay, so for ASC we have to consider the steel beam, and for this AST again we have to consider singly reinforced beam plus doubly reinforced, that is a steel beam. Okay, so this is a problem. I hope you understood this problem. So solve these two problems, this problem and the problem which you solved in the previous class. So these two problems you can practice. So these are type 2. So in type 1 problems we have solved how to find out the moment of resistance of doubly reinforced beam. And in type 2 it is finding out AST and ASC. Okay, so this will complete the analysis of doubly reinforced beam. Okay, in doubly reinforced beam, two types of problems you have to practice. So in the next class we'll start with the analysis of T-beam, okay, or flanged beams. So thank you very much for attending this session. Okay, if you have any doubt, feel free to ask me. Okay, so thank you.